this is a good problem to get us comfortable with the mean value theorem and how to approach a theorem in general, looking for being very particular about how it's implemented. So it's asking me to state A, whether or not the function satisfies the hypothesis of the mean value theorem on the given interval, and then B, if it does, find the value of C in that interval that satisfies this equation. Well, let's take a look at the mean value theorem. Mean value theorem says if y equals f of x is continuous at every point of the closed interval and differentiable at every point of its interior. Now you'll notice that this is not a closed interval there. It is an open interval. That's because if I have a closed interval AB, the A and the B are going to be endpoints, and endpoints are not differentiable. So if those two things are true, then there is at least one point C in that interval where the derivative at point C is equal to the slope of the segment or chord that runs from point A to point B. So in order to answer the first part of the question, whether it satisfies, whether my function here satisfies the hypothesis of the mean value theorem, well, what that's asking me is I'm looking at the hypothesis of the mean value theorem, and I first have to determine, is it continuous at every point during that interval, and is it differentiable at every point of that interior? So to do that, I'm going to look at the domain of the function, and I'm going to look at the domain of the derivative, because those will both tell me whether or not, well, if it's continuous, that means that it's not going to have any points of discontinuity in the domain of the function. And if it's differentiable, then when I look at the domain of the derivative, that will also have no points of discontinuity. Both of those we use don't ride lions, the denominator, radical sign, and logarithm, to determine the domain of those two items. So you see that is laid out right here in these first 5 steps. So let's go back to our function. And I want to look at the domain of this function. For purposes of that, I'm going to rewrite it as the cube root of x squared. Now I don't have any denominators. I do have a radical sign, but the index is odd, so I don't really need to worry about that. And I have no logarithms. So the domain of this function as a function would be negative infinity to infinity, all real numbers, so it certainly is continuous on that one little tiny interval. Well, let's see if we can figure out what the derivative is. So I'm going to use this format here. So the derivative would be equal to 2/3 x to the 2/3 minus 1. So that is 2/3 x to the negative 1/3. So there's my derivative. And if I'm going to rewrite it as 2/3, well, I'm going to rewrite it like this. I'm going to rewrite it as 2 over 3 times the cube root of x. So in looking for the domain of this, then I can see, well, there is a radical sign, but again, it has an odd index. But I also have no logarithms, but I do have a denominator. And I can see that x cannot be equal to 0. Well, does that cause me a problem? The question is the function differentiable on the interior AB? Well, since in this particular function I'm looking at it from 0 to 1, the interior would be 0, 1. So even though in the domain of the derivative, x cannot be equal to 0, that still means it satisfies the mean value theorem because I'm looking to see whether it's differentiable over the interval 0, 1, parentheses, so not including 0. So I'm still, this function here over this interval does satisfy the hypotheses of the mean value theorem. Just so we can see this a little bit better, I'm going to graph this function in Desmos. So here is the function. And now I've restricted the interval to between 0 and 1 inclusive. And now I've zoomed in on it so we can look at it a little bit better. I'm trying now to find the one x value c such that f of b minus f of a divided by b minus a is equal to the derivative of the function at c. What's this say? What's this telling me? Well, let's kind of go back to our graph here. If this is a, and over here at 1 is b, so I have the closed interval 0, 1, right? Then this point right here is the point a, f of a, and this point right here is the point b, f of b. Well, if I'm looking to find this, if I'm looking to find this right here, isn't that the same thing? Let's change this here to x1 and x2, and this would be x1, y1, and this would be x2, y2. Isn't that the exact same thing as y2 minus y1 over x2 minus x1? Very familiar to you as the slope. So what we're trying to find here is, on the one hand, I'm going to have a chord that goes between these 2 points right there, and that's going to have a particular slope. And what the mean value theorem says is that there is a tangent to the curve at some point in this interval that is going to have the exact same slope as this point that we've just done to connect the two endpoints. So how we're going to find that is, first we're going to find the point f of a, then we're going to find the point f of b, and then then we'll have enough information to tell us the slope. So here again is my function. This is my a, this is my b, or we can make it little a, little b. So what is f of 0? Well, f of 0 is 0 to the 2/3 power, so it's equal to 0. So f of 0, that point is going to be the point 0, 0. And if I look at my graph, that certainly looks like that's the point right there. How about f of 1? The other end, the b. F of 1 is equal 1 to the 2/3 power. Well, that's equal to 1. So that point is going to be equal to 1, my x value, 1, my y value. And again, looking at the graph, that seems to make a lot of sense. So what then is f of b minus f of a divided by b minus a? What is the slope of this line segment, this chord right there? What is the slope? Well, that should be pretty easy. I know f of b is 1, and f of a is 0, so 1 minus 0, and b is 1, and a is 0, so I have 1 over 1. My slope is 1. So now that I know what the slope is of this entire line segment, this entire chord right here, I want to find out where on the function, here's my function, what x value also has a tangent that will be parallel to that will have the same slope. In other words, at point C, my derivative of the function at point C, f prime of C, has to be equal to 1. Well, I know that my f prime of the function is equal to 2 divided by 3 times the cube root of x. I found that out a little while ago. Well, I'm not finding f of x now, I'm finding f of c. So that is telling me f of c would mean that 2 divided by 3 times the cube root of c, well, that has to be equal to 1. That's what I'm trying to find out. I want to make sure that the slope of this is equal to 1. Well, let's solve. I think I'm going to multiply both sides of this equation by the cube root of c. And that gives that, so the cube roots of c cancel out, so I have 2/3 is equal to the cube root of c. And now I'm going to cube both sides. So I have c is equal to 8/27. So what this is telling me is that at the x value of 8/27, the slope of the tangent right at that point is going to be equal to 1, which will be parallel to the slope of this right there. And this is how you write it out in prose. And I'm going to be asking you to do this. The tangent to f of x equals x to the 2/3 at x equals 8/27 has slope 1 and is parallel to the chord joining A, 0.00, and B, 0.11. So just to check my work here, I want to find out what is f of 8/27. I want the y value there. So that means I have 8/27 to the 2/3 power. Well, I know that the cube root of 8 is 2, and if I square that, I get 4. And the cube root of 27 is 3, and if I square that, I get 9. So I should have the point on my graph of 8/27 for 9ths. And that means that the slope of the tangent line, the equation of the tangent line, should be y minus y1 is equal to m, my slope is 1, times x minus x1. So I took that and I plugged that into the Desmos, and as you can see, there's my here's my piece of the function right there, and here is my tangent line, and it hits right there at the point 8/27 right there, and it is perfectly tangent. So in fact, I did the problem correctly.